Hello class, we're going to discuss potential energy. Now whether you knew it or not, we dabbed a little bit into potential energy with example 6.2. Work done by gravity is mgh. We define mgh as gravitational potential energy. Note that h is the same value as y for variables. Another way to think of potential energy is energy that is stored. An object lifted to any height above the ground has stored energy because as soon as you drop or let go of the object, it moves. When an object falls, energy is transformed from stored gravitational potential energy into kinetic energy, the energy of motion. One thing to remember is that you need a reference point for potential energy. In the figure to your left, y1 is the reference point where potential energy equals 0. Typically, we set the ground as a reference point so that the ground has 0 potential energy. But you can set the reference point anywhere, like a table. If the object is above the table, your potential energy is positive. If your object is on the table, the potential energy is 0. And if the object is below the table, then the potential energy is negative. For our first example, we have a 1,000 kilogram roller coaster car that moves from point 1 to point 2 and then to point 3. What is the gravitational potential energy at points 2 and 3 relative to point 1? Meaning, take y equal to 0 at point 1. The first step is to start off with our new equation for potential energy, which equals mgh. From there, it's just a plug and chug, but take a closer look at what we plugged in. Since point 1 is a reference point where potential energy is 0, that means point 2 is only 10 meters above point 1. And when we chug, we get a positive 9.8 times 10 to the 4th joules for potential energy. However, at point 3, it's 15 meters below point 1, so h is negative 15 meters. Now, when we plug and chug, we get negative 1.5 times 10 to the 5th joules. The change in potential energy is just the difference of potential energy between point 3 and point 2. Plug and chug, and we get negative 2.5 times 10 to the 5th joules. Now for part B, for part C, it asks us to repeat part A and B, but take the reference point to be at point 3, and set that equal to 0. Now if we repeat the whole problem, but take the reference point at point 3, of course our potential at point 2 and point 3 would change values, and obviously point 3 is 0, but notice that the change in potential between point 3 and point 2 stays the same value. So no matter where you pick the reference point for potential energy, the change in potential energy between 2 points always stays the same. Another type of potential energy is elastic potential energy. Elastic potential energy can be created by springs. When you compress or stretch out a spring, you're storing energy, because as soon as you let go of the string, the object begins to move. And once again, stored potential energy transforms into kinetic energy. The force exerted by springs equals negative kx. K stands for the spring constant. The larger the value of K, that means the stiffer the spring, whereas the smaller value of K means the flimsier the spring is. And X represents the displacement away from the spring during its relaxed state. The reason the equation is negative is due to the direction of displacement and the spring force pointing in opposite direction, as shown in examples B and C. The equation for elastic potential energy is 1/2 kx squared. This equation is derived from analyzing the area underneath the spring force graph versus displacement. This area represents the amount of elastic potential energy stored. However, you just need to know how to apply the equation. In this course, we will not go over non-conservative forces, but if you're planning to take an AP course In the fall, please take a look at this section. Now, with no non-conservative forces, the sum of the change in kinetic and potential energy equals 0. And we'll define the total mechanical energy as E, and that is kinetic plus potential energy. And since the energy is conserved, that means that the initial total mechanical energy equals the final total mechanical energy. Here's an example. The rock has some value of total mechanical energy E, and that value never changes. And mathematically, we can calculate E by using the equation over to our right. Notice how the figure to the left shows the rock transforming all potential to all kinetic energy, but the total mechanical energy of adding both kinetic and potential energy never changes. Another example is that if there's no friction, the speed of the roller coaster will depend only on its height compared to its starting height because of conservation of energy. Alright, let's do an example. If the initial height of the rock, which is y1 or h, equals 3 meters, calculate the rock's velocity when it has fallen 1 meter above the ground. First step, we'll write out the conservation of energy for initial kinetic energy and potential energy equals final kinetic energy plus potential energy. The next step is to cross out any values that are 0. In this example, we only have the initial kinetic energy equaling to 0 because the rock is dropped from rest. Next, write out the equations for kinetic and potential energy with the initial and final subscripts added appropriately. Look at that. Mass cancels out. So our equation reduces. And now we just solve for the final velocity. Then we just plug and chug to get 6.3 meters per second for the final velocity of the rock hitting the ground. In our next example, let's assume that the height of a hill is 40 meters and that the roller coaster starts from rest at the top. We want to calculate the speed of the roller coaster at the bottom of the hill. Again, we'll start off with conservation of energy. This time we have initial kinetic energy and final potential energy equaling to 0 because the car starts from rest, and the bottom of the hill is our reference point for 0 potential energy. Now we can plug in the equations for kinetic energy and potential energy. And again, mass cancels out. Our equation reduces down a bit. Solve for the final velocity. And we plug and chug, and we get 28 meters per second as the final velocity. Now for part B again, start with conservation of energy. But this time only initial kinetic energy equals 0 because it starts from rest. Plug in the equations for kinetic and potential energy, and mass cancels out, so our equations reduce, and this time we're solving for the final height. Plug and chug, and we get 30 meters. Now notice that I plugged in 14 meters per second for the final velocity because that's half of 28 meters per second from part A. Here we have two water slides at a pool that are shaped differently, but the start of the height is the same. The two riders start from rest at the same time, but on the different slides. Which rider, Paul or Corny, is traveling faster at the bottom? And the answer is that they both have the same speed when they reach the bottom of the slides because of conservation of energy. The initial potential energy all equals final kinetic energy. And if we were to solve it mathematically, it only depends on the height to solve for the final velocity. Now with elastic potential energy, the total mechanical energy is still conserved. In this course, we'll either do gravitational or elastic potential energy when using conservation of energy, and not both. However, if you plan to take AP, please take a look at how to use both in the book. In this example, we have a dart with a mass of 0.1 kilogram that is pressed against a spring in a toy dart gun. The spring has a spring stiffness constant of 250 and it's compressed to 6 centimeters and then released. If the dart is detached from the spring when the spring reaches its natural length of x equals 0, what is the speed that the dart acquires? Just like we've done before, use conservation of energy. In this example, the initial kinetic energy and the final potential energy is 0 because the dart starts at rest, and when the dart leaves the spring, there is no elastic potential energy because the spring is relaxed. Now we plug in our equations, but this time the elastic potential energy, and not gravitational potential energy, and then of course we have our kinetic energy equation. And the 1/2 cancels out. Our equation reduces down a bit, and now we can solve for our final velocity. Plug and chug, and we get 9 meters per second squared 9 meters per second for the final velocity of the dart.